welcome. My name is Cody. I'm from LASSO, and today I want to show you Project Hyperspace. Project Hyperspace is a project created out of our company, out of our own big data science needs, while we've been doing machine learning for simulation data. Nonetheless, we also found it quite interesting and useful for other domains. So stay tuned, even in case you're not from the simulation branch. Now, how did we start? In the beginning, we just did, as many people do, some machine learning research. We did dimensionality reduction, we did reduced auto modeling, neural networks, graph-based neural networks, for different purposes. Sometimes we wanted to predict simulation results. Sometimes we just wanted an overview with simulation embeddings. So the use cases have been varying. Nonetheless, we found in all of these very occurring patterns where we really struggled, and also the existing machine learning and frameworks and solutions were not really specialized for simulation data, which usually has very heavy tensors. So we started on forming our own solutions and approaches step by step, and out of that came Hyperspace. Now, building machine learning pipelines is really hard in our field, and it is so because, yeah, you could say the program landscape is very tough. We have mostly a strong third-party application field where you need to use certain applications in order to access the data at all. But those programs, they force you to go into them, right? They want you to work in them, and then they have an old Python version where you don't have TensorFlow. Then you need to interface it. It doesn't work. It's very tough to work with these third-party apps actually in real life, and it has been making it quite difficult. Though nowadays it's getting better and better. These companies and community in general has been learning, and new best practices are step by step established. Still though, they're very far away from what data science really is nowadays. Also, we have certain executables which eat very awkward formats, and incorporating that with your own Python scripts is really tough sometimes. Like, it can take a lot of time just to get it working. And this is really what pushed us into creating our own framework in order to automate it. Now, the biggest issue, or one of the biggest issues we have, is service connection. Connecting these programs is no fun at all. They communicate mostly through very complex file formats. You need to call them with a lot of special arguments. They're not necessarily very good at batch execution. Some might need certain hardware to be executable in batch, such as needing a GPU or something. So it is very tough to actually get these pipelines running. And even if you get them running, often they're made up of some scripts, and those pipelines are largely untested. So it's very tough to keep an overview where failed something, what failed. It's just a very complex way to interact. The data transfer has been, for us as data scientists, as painful as you can think of. Data transfer in especially simulation area is mostly file formats. And we have a ton of problems with the formats. First of all, everyone is often writing its own format, which is not readable at all because it's a proprietary format, which is okay because usually you can evade to specialized formats or other formats, or even write your own format. But this takes time. For example, the issue with specialized formats is they have their own way of describing the data, and sometimes I want to transfer more attributes or remove some to make it faster, and this might not necessarily be possible. So the formats also are often so complex that they're incompletely supported by libraries, and so it's not so straightforward to simply use a library and read in that format, because this format has been developed from 1970 on, and it has not been modernized, you could say, to, for example, JSON or YAML files. Now, the next thing is also there's sometimes interface library, but they also don't support the standards totally, or they cost money, which also is very limiting for machine learning research because many researchers don't have the resources to actually buy these libraries or these expensive tools. And in the end, we still need to remember we are dealing with file-based I/O. File-based I/O is highly inefficient. So we are kind of fighting a lot just to get the worst level running. And this has been very unsatisfying for us why we went forward with Hyperspace. In the end, also scaling has been bothering us. Parallelizing a script is time consuming. You need to spawn workers. Those workers need to be secure in terms of RAM and CPU, otherwise they kill your machine. Then you also need to save in between in case you process a lot of data. There are many issues which we tackled, and you will see in Hyperspace or get explained why we did certain things and how it fixed it. Now, also what we often do is for higher performance, we need to evade into a different programming language such as C++. Sometimes we have a data pipeline and one Python script doesn't really give the performance which we need, so we need to evade into C++. And combining different languages is very tough, especially also sometimes we want to do web programming or Node.js for visualization. So it's a very tough thing to actually combine these different languages which have been designed for their purpose, but which were not so easy to interface still nowadays. So Hyperspace has been built to address especially these issues. It's a data science oriented solution. So it's very different from your standard process control where you just execute program after another. We focus more on the data science aspect. It has grown from our internal needs, as I said, and it is just meant to especially process heavy tensors. We found heavy tensors in a few years ago very hard to process because the frameworks mostly are designed to process lighter tensors, such as images, which only have a few kilo at maximum megabytes, right? And we are dealing with hundreds, not gigabytes of tensors. Now, also parallelization has been so annoying to do manually that we found it to be necessary to create our own approach on it and to make it easy to distribute your idea to thousands of data files and sets and whatever you need to process. In the end, we created also web-based UI because it makes it very simple to access it, and I can access it from some machine which is not necessarily as strong as I need it to be, but then the back end, of course, of the server then does the heavy lifting, and it's in a high performance environment, so we don't have to care so much anymore. Now I will show you some live demo feed, and we will introduce you to some basic of the features, and we will show you how basically Hyperspace works. Please stay tuned. I hope you will enjoy it, and here we go.
A flow is nothing else than the execution of programs and scripts one after another. This demo will show only a few nodes, but in general it is possible to incorporate arbitrary programs into the pipeline. In the beginning we have a so-called JSON node, which we often use for configurations. The variables of the JSON node are then forwarded to a Python node, which itself then formulates some outputs, and they will again be forwarded to further processes in the data pipeline. The variables are strongly typed so that the data pipeline stays consistent and the inter-process memory transfer is safe. This direct memory transfer is a big contrast to program pipelines in our domain, which only read and write files. Not only is this very slow and inefficient in case of bigger data structures such as 3D meshes, but also the file types might not necessarily support the attributes which we want to transfer. Note that we also follow the big data principle to bring your code to the data and not your data to the code. This makes a lot of sense, since usually your machine would have to suck in all the data, process it, and spit it out again, which is very limited, especially when the data amount is very big. Here we might not even necessarily transfer data at all, because we can bring these nodes to the place where the data resides, eliminating the data transfer almost entirely. A flow graph can be executed by simply pressing the run button. This will spawn a so-called session. A session is nothing else than the processing of a flow graph. A session graph like here must not necessarily look the same as a flow graph, because due to parallelization, as you will see later, there might be deviations and more jobs might be spawned. Here you can inspect print information, failure information, and are also quickly taken to where exactly your programs failed. In case of many jobs, thousands of jobs, often the job table here helps a lot in order to filter quickly out what has been going on and where to actually improve. Please note that we built this especially because of its failure redundancy capabilities. For example, imagine you process 1,000 files and 2 are ill-formatted and you cannot do anything really about it because it's coming from the outside. Then you don't want your entire process pipeline fail and need to restart just because those 2 files were ill-formatted. And this is exactly why we built this, because this gives us the capabilities to restart jobs somewhere in between and also not having to restart the whole data pipeline at all. Here we will show you how Hyperspace actually handles parallelization. What we often encounter in practice is that you have a file written to process a single sample of a dataset, here one file of many. And then you want to distribute it and do it on thousands of files. The issue what we have is then often you need to spawn a multiprocessing pool, need to be aware of your resources like RAM and CPU and network bandwidth. Then you need to go ahead and process those files, and in case of any issues you also need to program to write a log, make a restart point of your data, and so forth and so forth. It's just all the time the same work because we are lacking process control. That's why we implement this split node, and split node is very, very useful and is kind of designed to tackle this problem. What it takes in is a list of something. It doesn't matter. Here it's a list of strings representing file paths, and what it spits out is a single file path or a single string here, and it lets us process each sample individually. So you can think of this as a for each loop. And what it does then, it spawns all the processes in the rear to process each of these files. So we can simply use our prototype script, punch it into a split node, and then we are totally ready to go. Also pretty cool is when you run it, you will actually see that the whole flow graph is not 3 nodes anymore, but it's actually 7. So all of these jobs here have been spawned in parallel, and that's what I said before. The session graph can, because of the splits, deviate from the flow graph because you have all these parallel jobs. Now we also though have complementary to the split node, we also have the so-called join node. In this flow here, we have a list of numbers being splitted, printed individually, and then also joined back into a whole list again and then printed out. This is just for demonstration purposes how the feature actually works. So we have the list in the beginning. We see that all the individual entries can be printed individually, and then here after the join node, of course, we have the list back in the hand. Of course, this could also be some results which we obtained by processing individual samples or files ranging from statistics or to extract its metadata or whatever you want. An advanced usage of the split node is to use it in parallel. What we have here is a flow to train a neural network with different hyperparameter combinations, which is the number of layers and the number of subsamples used for a point cloud. What you do then is also print out some statistics about the training process. Now how do we achieve this? Now we have here the JSON node, which has the different number of layers programmed in. We want to try 1, 2, or 3 layers. Then these parameters will be run through the split node, and what happens is if those 2 splits meet, they try out all combinations, or rather said, it's a for each in a for each loop. Like all of these combinations from both split nodes will be exercised and a job will be spawned to try it out. This makes it very easy and useful to add new parameters and then job the corresponding amount of jobs. And you can see this actually in a session graph which happened. Here you have both split nodes, and from both split nodes all links go to one of these training network nodes. And then in the end you have the printout where you have the parameter combination as well as the training time. Of course, the network can be saved in those nodes too, or is saved, and then you can use them afterwards for different evaluations too if you like. In the end, let us show you how a real-world flow looks like. Here in the beginning we have some settings from which we collect files, and those files that are then processed individually. Those files are simulation result files coming from a crash simulation, so they are quite heavy. What we also do is we process the first file differently from all the others and feed that data into processing all other files. So see that some data is flowing around the split and some is actually flowing through a split. And it feels very native actually using this without really having to think about if it's possible or not. Then we join the results back together, do some machine learning, and create a web report in the end for the user.
Welcome back. Now, what we've been targeting with Hyperspace was what you see on the left side here, the data science branch as a whole, right? We focused data serialization, so you don't have to worry about the data formats anymore because memory is transferred directly, right? About storage and retrieval, you can easily use code blocks or APIs to also access databases or file systems, whatever you need. You will have access to anything you need in machine learning in most of the languages. And also in the end, deployment is just one button. This is very important to us because this usually in the real world is a lot of work. What we have not been addressing yet though is communication and visualization within this framework. This has been because this is a very domain specific problem. So we thought about excluding it and creating another solution eventually for it. It's still a work in process. Now what's coming? We've been going on and multi-language coding is still in its infancy, but it will be online and we are really targeting for it. Because for us it's important that every code block just runs and what it inputs and outputs. We don't want to care anymore what language is actually running inside, and it makes a lot of sense, and that we can easily interchange certain elements in our processing pipelines without having to worry about the compatibilities of the languages, for example, especially often when we have a library in another language we want to use and so forth. It's just so freeing if you have this feature. Also, creating web services from flows is a very cool thing we're aiming for. Web services would make it available to your flows through an API or something, so people from the outside can trigger it and can more easily access your knowledge. And you can also provide these services to other people which might then use them. In the end, a node library is also very important to us. We have quite a few nodes on our own already, but we think it's best if you not only have to code your own nodes all the time, but that other people might do this and provide their code blocks or their nodes then for you, and they can also be rewarded for it. So it's very important for us, and it would just leverage the knowledge of the community much more than it is already done right now. In the end, customizing your workers to run any program you like is very important also to us, because in the simulation domain you have so many customized programs that you need to be able to spawn your worker or whatever you want, or your own Docker images with the certain inputs which you like. Now, in case you're interested, please let us know. The solution has been growing out of our own needs, but it's also important for us that you tell us what your needs are, because in any case, we might open this up in the future. We want also it to be ready for you, and that your desires and needs will be covered, and that it will be not just a narrow island solution, because there are a lot of opportunities and possibilities in this framework to alleviate a lot of the burdens which we have every day when creating actually data pipelines. Thank you very much. I hope you enjoyed the presentation. Please like it if you like it, and see you soon.